Hello, and thanks for being here. Welcome to Applications in Climate Science Using Earth Engine. I'm Nick Clinton, a developer relations engineer on the Google Earth Engine team, and I focus on helping scientists use Google Earth Engine for social and environmental impact. My background is primarily in remote sensing, specifically land cover, air quality, and emissions, and it's really exciting that we get to collaborate with the scientists like the ones you'll hear from today. Climate science plays a critical role in understanding climate change and solutions for climate action and grounding those solutions in science and validation. Earth Engine can be very helpful in analyzing a huge amount of climate data, global data, oftentimes at very high spatial and temporal resolutions. In this session, you'll hear several scientists present on projects where they're using Google Earth Engine to build and analyze climate-related data sets, such as for air quality, urban heat island, climate stress, and more. First up, you'll hear from Youchen Shen, a PhD candidate at Utrecht University, who will present on how she has used Earth Engine for air quality modeling.
Hi, my name is Youchen Shen. I'm a PhD candidate at Utrecht University in the Netherlands, and I'm going to talk to you about how we use Earth Engine to estimate annual average air pollution concentrations for the whole Europe from 2000 to 2019. And our team includes Kees de Hoog, Gerard Hoek, and Rolf Vermeulen at Utrecht University. And this work is funded by an European Exposome project called EXPANSE, short for Exposome Power Tools for Healthy Living in Urban Settings. And we are also in close collaboration with Google. So first, we will go through why and how we model air pollution, and then we will look at how we implemented our work in Earth Engine with some code demonstrated. And then finally, I will share the impacts of using Earth Engine in our work. So the problem we have for European-wide health analysis studies is that we need harmonized maps for the whole Europe, spanning from multiple years to better evaluate life course health effects of air pollution. So from our previous European project, ELAPSE, we have air pollution estimates for 3 historical years as for most European countries, as shown in the upper image here. So based upon this, we want to improve the air pollution maps by covering the whole Europe, as shown in this lower image here. And then we also aim to cover for the period from 2000 to 2019. And in order to achieve these goals, we would need time-varying geospatial data and some geospatial algorithms for air pollution modeling. So before we dive into how we use the Earth Engine for air pollution modeling, let's get some basic idea of the commonly used empirical method for air pollution. And this method is called land use regression. In short, there are 3 main components. The first is the air pollution measurements that we want to estimate. These measurements are measured at monitoring stations across Europe. And the second component in the algorithm is the geospatial predictors we use to explain the variations in the pollution concentrations. And then the third is the algorithm that we use to explain the variations in the pollution concentrations and the geospatial predictors. So after training our algorithm, we then use the geospatial predictor maps to estimate the air pollution concentration surfaces. So traditionally, researchers would download the geospatial data online and then process the data in their local computer. But such work demands large storage space and computation power when the spatial and temporal scale are large, like our study, which covers the whole Europe for a 20-year period. And this is where Earth Engine comes in handy, because we can store and process all our predictor maps and produce the air pollution concentration maps all in Earth Engine. So these are the geospatial predictors we used in our study, and they include both spatial and spatial temporal variables shown in these two columns. So some variables are available in Earth Engine data catalog and some are not. So these are the variables available in Earth Engine, including Korean land cover data, altitude data, the ERA5 meteorological data, and the aerosol optical depth from Terra and Aqua. So then these are the variables that are not available in Earth Engine. So we upload the data to the Earth Engine platform. So these include the road data from OpenStreetMap, impervious surface from Copernicus, the population data from the European Commission, and some predictions from the chemical transport models, as well as the some satellite observations that are not available in Earth Engine. So for the algorithms, we use 3 algorithms ranging from a simple linear regression model, a geostatistical method, and a machine learning method. And these algorithms can all be implemented in Earth Engine. And this is our workflow of the study. First, we collected and processed all our predictor maps in Earth Engine. And then we extracted the predictor values at the monitoring stations so that we can use the values to train our algorithms in R. Then after training our algorithms and evaluating the model performance, we then put our model results back into Earth Engine to create our air pollution exposure maps there. And here are some code that we used for geospatial data processing and visualizing the results. So for some geospatial predictors, we need to compute for the sum of the values within a circular buffer to capture the dispersion patterns of the air pollution. So we computed this buffer predictor values using the reduced neighborhood function in Earth Engine. And for the visualization, we created a function that can animate the annual average prediction maps. And this function was modified from these 2 sources, and it requires a package created from another user. So this function requires input for the image collection of the maps to geometry objects to indicate the location of the title and the gradient bar. And also we would need the area of interest to indicate the region and the number of frames shown per second for the animation. So after preparing the elements for the animation, UI.thumbnail function is used to create the animated image. So this is an example output of the visualization code. It shows the nitrogen dioxide concentration from 2000 to 2019. And this gives us a clear visualization of the spatial temporal variations in nitrogen dioxide concentrations for the whole Europe, ranging from 2000 to 2019. So in conclusion, Earth Engine impacts our research from 2 parts, the data processing part and the visualization and result output part. So first, all our geospatial data was stored and processed in Earth Engine. And at the end, the total size of the final data sets is more than 300 gigabytes. So using Earth Engine not only save our local storage space a lot, but also our efforts and times for processing the large geospatial data sets in our local computers. And secondly, after getting the optimized algorithms in R, we can produce the prediction maps and visualize the maps within a minute. And this enables us to visually check for potential anomalies in the output maps quickly. And this check is important because, as suggested in our previous study, both visualization and validation are essential for evaluating the quality of the air pollution maps that are going to be used for our health analysis study later. Now you might think, with Earth Engine, our modeling work seems so easy, but there are actually parts that we cannot do in Earth Engine, such as building and optimizing the algorithms. So all the model training and optimization are difficult or time-consuming to be done in our Earth Engine for our study. And that's why we did this part in R. And we have also spent a lot of time and effort in optimizing the algorithms to produce maps with satisfactory prediction accuracy and with reasonable spatial patterns. But all in all, Earth Engine does facilitate our modeling work a lot in the other two parts of our work. So if you have any questions or want to know more about our research, you can reach me via this email. And we would also like to thank Karen Toxin-Batman for inviting us to share our work in the Geo for Good Summit 2021, and thank Nick Clinton for helping us to implement our work in Earth Engine during the process. Thank you all for your attention.
All right, thank you very much, Youchen. Our next speaker is T.C. Chakraborty, an Earth Engine scientist from the Pacific Northwest National Laboratory, who will present on how he has used Earth Engine for urban heat island mapping.
Thank you for the introduction. Hello again, everyone. I'm TC. I'm an Earth scientist at the Pacific Northwest National Lab. Before this, I finished my PhD from Yale University. And today I will be giving an overview of some of the work I've been doing over the past few years on examining urban heat and particularly urban heat islands using satellite observations. So you may all know that the world is rapidly urbanizing, and you can see this from the animation here for country level land cover for urbanization from 1992 to 2018, as well as for the changes in the urban extent for individual cities all around the world. One of the consequences of this increasing urbanization is the urban heat island effect. This is the phenomenon where cities are warmer than their surroundings. And if a city is warmer than its surroundings, that means that there is higher heat stress, higher energy use for cooling down the buildings, as well as higher secondary air pollution. And this is important not just for now, but also in the future. This is for two separate reasons. As the world continues to warm, you will have higher fraction of extreme heat events. However, if you are in an urban area, you will have an even higher fraction of extreme heat events. Moreover, there will be more people living in urban areas in the future. In fact, roughly 2/3 of the global population will be living in urban areas by 2050. This means that you're looking at a higher proportion of the global population being exposed to higher heat events in the future due to urbanization. So a couple of years ago, we worked on mapping the surface urban heat island intensity, which is the urban heat island as seen from satellites using Google Earth Engine at a global scale. For this, we developed an algorithm called the Simplified Urban Extent Algorithm. I'm going to give you a brief overview of this algorithm. Basically, we start with urban cluster boundaries, and within each boundary, we have urban land cover data. So this land cover data can be from anything, and it depends on the accuracy you want and the resolution you want. So here I'm showing the MODIS land cover data, but I have since moved on to the European Space Agency's Climate Change Initiative land cover data. Based on this land cover data, I can separate out the pixels into urban pixels and non-urban pixels. Then the difference in the temperature or the land surface temperature between the urban and the non-urban pixels gives you the surface urban heat island intensity. Based on this method, we calculated urban heat islands from 2003 to 2018 for every month. So from this, you can get diurnal trends, you can look at seasonal trends, and you can also look at temporal trends, long-term trends. The dataset itself is now available on the Earth Engine data catalog if you want to use that for your work. We also created this web application to explore the data and download the surface urban heat island intensity for cities of interest. You can see a screenshot here for the Chicago urban boundary. There's also a QR code if you want to access the web application right now. So one of the advantages of having land surface temperature from satellites is that you can get spatial variability, which is very hard to get from air temperature measurements. You can never have enough air temperature measurements in cities. And using this land surface temperature data, we wanted to look at disparities in surface urban heat islands and thus land surface temperature within urban areas. For this, I used the algorithm I described earlier to calculate the surface urban heat island intensity for 497 urbanized areas in the US at the census tract level. Then we looked at the correlations between the surface urban heat island intensity versus median income of the census tracts. And you can see here that most of these values are negative. That means that the surface urban heat island is higher for census tracts with lower income. And this was true for 85% of the urbanized areas. So this is not just true for income, but also for race. When we looked at the 175 largest urbanized areas, we found that in 96.5% of the cases, the surface urban heat island intensity was higher for people of color than for non-Hispanic whites. You can see this from the map here, where it's worse for people of color in all of the cases where you have triangles, and almost every one of them are triangles. So similar to the global surface urban heat island data set, we created a web application to explore this disparity. And you can go to the QR code if you want to look at the data. In parallel to this work, it's becoming increasingly obvious there is a large gap in tree cover between higher and lower income neighborhoods within US cities. One of these studies was published this year from a group from the Nature Conservancy, where they looked at like 5,000 cities and found that like 92% of the cases there was lower canopy cover in lower income census blocks. I met one of the lead authors of this study at the 2019 Geo for Good Summit, and we discussed how to use all this satellite-derived information to provide a way to reduce the surface urban heat island intensity as well as the tree gap. So for this, I've been working with the Nature Conservancy on a project which we call QT, which is, I'm going to get to later, but we started with cities in California, roughly 200 cities. And in this plot, we show similarly the correlation coefficients between the surface urban heat island and income, which as you expect is usually negative. Surface urban heat island and canopy percentage, again negative, because higher canopy percentage reduces land surface temperature, and then canopy percentage and income. And you can also see the cities with the highest tree gap, which is given by the difference between the highest percentile tree cover and the lowest percentile value. And then, yes, now we are using the satellite information to figure out how much space is actually available for urban afforestation. This is important because even though it's known that urban vegetation reduces local temperatures, there is normally not enough space in a lot of urban areas for tree planting. And so we call this, again, QD, closing urban tree cover inequity. I'm going to give an example here for Los Angeles, where you start with the tree gap itself, which is the tree cover percentage of the census block group subtracted by the tree cover percentage of the highest income percentile census block group of the city. And here there is a ratio of the space required to close the tree gap to the space available for afforestation. So as you can understand, if this exceeds 1, there is not enough space in the census block group to completely close the tree gap. But you can see that in most cases, you do close the tree gap. but not for a lot of the census block groups in the middle, which makes sense. A lot of the very built up census block groups wouldn't have enough space, enough pervious surface for planting trees. Then we look at the space available for closing the surface urban heat island gap versus the space available for actual tree planting. And here you can see that we can not really close the surface urban heat island gap completely using just afforestation. We can close it partially, but that makes sense because the lack of tree cover is not the only reason for the surface urban heat island intensity. Based on this information, which we calculated for roughly 200 cities in California, we can provide summaries of the benefits and co-benefits of urban afforestation. And I'm not going to focus on all of the numbers. There are a lot of numbers here. But overall, for 201 urban clusters in California, we have space for 1.4 million total acres of urban trees. And this would lead to annual benefits of over $1,000 million. And this would serve roughly 37 million urban residents. For the 69 cities for which we had a way to calculate the reduction in the surface urban heat island due to the increase in tree cover, we calculated an average reduction of 1.72 degrees Celsius. Now, note that most of this analysis till now has been done using land surface temperature, and that is not always equivalent to air temperature, which is what we care about when we are looking at heat exposure. So I have been also working with another colleague who I also met at the 2019 Geo for Good Summit on using crowdsourced weather station data to more accurately estimate urban heat exposure. So this study included over 50,000 citizen weather stations over Europe during the 2019 heat wave, July 2019 heat wave. And here for Paris, you can see the distribution of the citizen weather stations, and they're much more dense than anything you will get from standard weather stations in cities. But the important thing we found here was that there was a difference in the magnitude of the surface versus air temperature heat island. And you can see this both for the magnitude of the surface versus air temperature heat island, as well as the diurnality. So you see that surface urban heat island tends to be higher during the day, while the air temperature heat island tends to be lower during the night. This basically tells us that we should be a bit careful about using land surface temperature data from satellites directly for understanding heat exposure in cities. Right now, I'm using this crowdsourced weather station data in combination with the satellite data to understand how the combination of temperature and humidity modulates the heat stress within cities. That is all I have today. Thank you for your attention, and thank you, Google, for this opportunity to share my work.
Thank you very much, TC. Next up, we have Brian Smoliak, lead scientist for Reflective Earth, who will present on how he has used Earth Engine to quantify Earth's global reflective potential and local albedo changes.
In the next 10 minutes, you will hear about an effective yet underutilized tool to slow global warming, reflectivity. The idea of reflecting sunlight and the examples that reinforce it will broaden your perspective on climate action and inspire new use cases for Google GeoTools. Here's how we're going to get there. First, I will set reflectivity in the context of climate change. Then I'll tell you how Reflective Earth is distinguishing itself as a nonprofit organization. And finally, I'll show you a series of examples that leverage Google GeoTools to ramify our work on reflectivity. Along the way, we'll explore solutions from the scale of individuals to countries, culminating in a global view of reflectivity as one of many climate solutions. So to start, where does Earth's energy come from? Well, the sun, of course. Nearly all of it, in fact. Of the incoming solar radiation reaching the Earth, about 30% is reflected by the atmosphere and the surface, and 70% is absorbed by the land, ocean, ice, and air. This absorbed energy warms the surface and heats the atmosphere from below. And the Earth re-radiates this energy, some of which escapes back to space, and some of which is absorbed by the atmosphere and re-emitted back towards the surface. As greenhouse gas concentrations have increased over the past 150 years, more and more outgoing energy from the surface has been trapped in the system, leading to global warming and myriad other climate change indicators. Currently, Earth's energy imbalance is approximately 1 watt per square meter. And if you want to solve this problem, there really are 2 levers to counteract this imbalance. Increase the outgoing energy by reducing concentrations of greenhouse gases, or decrease incoming energy by reflecting more sunlight. Albedo is a scientific term for the ratio of reflected solar energy to incoming solar energy. It varies from 0, or total absorption, to 1, total reflection, and it's often expressed as a percentage. This animation was produced using the long-term median of daily MODIS imagery from Earth Engine, looped over the calendar year. At 500-meter spatial resolution, you can see the impact of precipitation and vegetation changes in albedo, but it is more difficult to see urban land use changes. For that, we need to zoom into the scale of cities. And here we see data from the World Resources Institute, who estimated reflectivity or albedo of buildings and roads in Los Angeles County, California. And it's really this what we're going to be driving at throughout the remainder of the talk. Reflective Earth is on a mission to slow global warming as fast and safely as possible by increasing Earth's reflectivity. You may have heard of climate intervention or geoengineering, which are deliberate and large-scale efforts to avoid the worst impacts of climate change. Unlike the centralized, top-down approaches that have been controversial in the public discourse, Reflective Earth is advancing a distributed, bottom-up strategy that invites people to participate in the process and encourages direct action in every community. This is a tool we are developing to allow users to explore the impact of reflectivity changes in their own area. Currently, the reflectivity optimization map allows users to drop a tile and see how changing reflectivity affects reflected sunlight in watts per square meter. So you can see how lowering the reflectivity or increasing the reflectivity can change reflection right in your area. Google Project Sunroof inspired us in the way that they overlaid solar photovoltaic potential in cities around the US. Building on Google Maps and Earth Engine imagery, we're building toward providing reflectivity insights around the world. We've connected with the Project Sunroof creators and the Google Cool Roofs team to explore this capability in collaboration. Using Sentinel-2 imagery in Earth Engine, we looked at a few commercial districts in Los Angeles to see how roof albedo changed in the past few years. These findings showed some albedo increases associated with cool roofs and also some albedo decreases. So you can see in that bottom image the sort of salt and pepper look associated with building white roofs and then some darkening of roofs as well. And here we used the Sentinel-2 surface reflectance product in Google Earth Engine. Here's an example of one building in the same neighborhood, viewed from aerial imagery from Google Maps on the left and Sentinel-2 satellite imagery on the bottom. And you can see the area of interest that we're targeting there too in orange. The time series shows albedo over the past 2 years. Note the rise in mid-2019, a slow decrease over the rest of that year, and then an increase followed by another decrease. And we were really interested in this time behavior, where you might expect that dust deposition over the course of the summer would reduce albedo, and then precipitation over the course of the winter might wash that away. But this persistent decrease really raised a question. And without higher resolution imagery, we were sort of puzzled. But Google Earth's timeline feature allowed us to see higher resolution imagery over time. And this prospecting revealed the original dark roof here on the left, the white roof installed in the middle, and then a progressive photovoltaic installation. You see the solar panels here on the far right. So this reveals an attribution challenge when it comes to albedo changes, and using the lower or coarser resolution data sometimes reveals challenges that we're still working on today. Earlier, I mentioned the scale of cities and the World Resources Institute dataset that we've been working with in Google Earth Engine. So here you see in the image buildings near downtown Los Angeles, and I've applied the inspector target to a building near downtown there. And you can see that albedo is about 17% as estimated by WRI. And we can also combine this with another data set that Reflective Earth has put together to estimate the reflected power by those buildings, both actual observed over the past few years, but then also the potential if that building were to have its albedo increase towards 1. The final thing I'd like to talk about today is at the scale of countries. And really at Reflective Earth, we ask the question, if you're going to increase Earth's surface albedo, where might you want to do that? And to do this, we use data from the European Center for Medium Range Weather Forecasting's most recent reanalysis product. That's ERA5. And here you see images of atmospheric radiation fluxes at the top of atmosphere, incoming, the fall equinox. At the surface on that same day, this is downwelling radiation, so more radiation in lighter colors and less radiation in darker colors. You see the surface upwelling, that's the radiation going back out towards space, and that's the reflected radiation. And then the radiation going out at the top of the atmosphere. And that's reflected by both the surface and clouds. And so at Reflective Earth, what we were interested in doing is applying a simple model of reflected radiation that decomposes the outgoing radiation into a component from the atmosphere and from the surface. And this considers both the initial reflection and then subsequent reflections between the atmosphere and the surface. And you note the Taylor series here. This follows the literature and will be forthcoming in a peer-reviewed journal article. And here we have reflectance, absorptance, and transmittance of this one-layer atmospheric model that we created. And you can see that the atmosphere is mostly transmittant of the solar radiation, so it mostly transmits it. There's some reflectance in the higher latitudes and in parts of the tropics. This is primarily clouds and dust. And then the atmosphere has very low absorptance, although it does absorb some of this solar radiation. So using this simple model, we're able to decompose or estimate the actual amount of surface reflected solar radiation reaching back out to space. And then we can also assume a perfect reflection of the surface over that square meter, and we can get the potential. And that potential surface reflected solar radiation is what we're really interested in. And that is what allows us to really zero in on particular areas of the world where you might want to focus your attention. So here I'm showing an animation that shows where we've uploaded this asset into Google Earth Engine, and we've displayed it, and we're looking around the world at that potential surface reflected solar radiation. And you can see the amount reaching back out to space as estimated by our model. Now, these areas, as I click around the world, show our areas where you might want to consider investing in these cool roof programs. So you see parts of the desert Southwest in the US, parts of sub-Saharan Africa, Chile, and parts of Australia and the maritime continent. So what this shows is that we're able to work with Google Earth Engine, and as we increase capacity, we're more and more interested in bringing these reflectivity solutions, combining it with the power of Google Earth Engine to really drive forward these solutions. So today, I've really talked about how reflectivity is a potential solution for global warming, and it's the fastest lever because it's instantaneous. As soon as you put that bright surface out there, it's reflecting sunlight. While we must decarbonize and reduce emissions and even pull historical emissions out of the atmosphere, I would encourage you to really consider reflectivity as a global warming solution. Thank you.
Thank you, Brian. Our next speaker is Brookie Guzder-Williams, Director of Data Science for the World Resources Institute, who will present on how he has used Earth Engine to model urban land use at global scale.
Hi, everyone. My name is Brookie Guzder-Williams. I'm the Director of Data Science at World Resources Institute. Today, I'm going to be talking a little bit about some urban land use work we've been doing. And in particular, I'll say a little bit about how we develop global scale models on Google Earth Engine and Google Cloud Platform. So I'll start by saying a little bit about the technology stack, and then I'll just dive into talking about our work, the input, the data, model and training. And then at the end, I'll talk about an informal settlement classifier we built using our model and do a little demo. So this technology stack probably looks pretty familiar to most of the people here. We're using Google Earth Engine for both data collection and also any data preparation we have to do for that model. For development and training, we're using TensorFlow to develop the models, and we're doing all of our work on AI platform, which I'm going to say a little bit more about in a second. And finally, we use Google Earth Engine for inference. And this is both great because when it finally comes time to deploy a global model, it makes it very easy to manage all of the jobs. But it's also amazing during development because it allows you to just go anywhere in the world and see what your model looks like there. And this has been really useful for me to kind of iterate upon the work I've been doing. So I did want to say more about using AI platform because I feel like this is a piece of the puzzle that a lot of people here might not be using. So AI platform notebooks, it's just a full Jupyter Lab environment. So of course you have access to Jupyter notebooks. But for me, I do a lot of, I make pretty charts, I do some analysis in notebooks, but I do almost all my work using Sublime and scripts. And, with AI platform notebooks, you also have access to the full VM. You can SSH in and you can run everything there. And then to actually do the training itself, I use AI platform jobs. And this is something I resisted for a long time because, well, it seemed weird. You have to package up all your data, and then you have to send it off to a cloud, and then they, spin up a VM, and then it downloads the data. And this all takes a lot of time. And it didn't make sense to me why I wouldn't just want to have my own VM and manage it that way. But I now realize how wrong I was. Well, there's a couple of things. For starters, when I'm using AI platform notebooks now, I only use CPUs. And the only time I ever use a GPU is when I launch an AI platform job. So this saves me some money. But what's more important, or what's been proved the most useful to me, is often I'll have a model and I'll have in mind, I'm going to do 5, 6, 7 tweaks to this model and try to decide which one is best. But I'm doing that in sequence, and each of these trainings might take 24, 48, 72 hours. And so it can take a really long time. And now with AI platform jobs, I can run all these things in parallel, and it can literally save me weeks of development. I will say that, my launch commands for these AI platform jobs look something like this, which didn't even fit onto the screen. And this was a little difficult to deal with. And so I built something which I can share a link to called AI Plat Go, which does two things. It simplifies the packaging of the data, but it also allows you to use, very simple YAML files to produce these command line. So diving into our actual work, we created, as our input data, we used cloud-free mosaics of Sentinel-2. And we created those cloud-free mosaics using S2 Cloudless. If you haven't used this, it's great. This was originally an algorithm that ESA put out, but the kind folks at Google Earth Engine have gone in and processed the entire Sentinel-2 cloud catalog. And so now it's very easy to create cloud-free mosaics of Sentinel-2 data. And then we upsampled this data to 5-meter resolution. And that was very important to pick up some of the finer details that we do predictions on. Our target data was Atlas of Urban Expansion. They have labeled 10-hectare circular locales in over 200 cities, and with open space, non-residential, and then 4 different residential categories that distinguish different levels of formality. And then we called everything that wasn't one of those categories a road. Now, because they're circular and because we're putting them into a neural network model, this kind of created a problem. And the way we solved this was by each time we go through a training loop, we kind of randomly place the circle in a different location. And this does two things. Because we're working with such small target areas, we didn't want to make it any smaller. And in addition, it acts as a data augmentation, and I think overall was a benefit to our training. This is our model architecture, which I'm putting in for people who want to see it, but I don't have too much time to discuss it here right now. And here's our final taxonomy. So again, when we were originally creating these cloud-free mosaics, it's 10-meter resolution, and it seemed like it was going to be hard to get too much detail out of it. And we were originally hoping to have maybe a 3-category model. But what we found was by training the full 6-category model and then rolling it up to 4, 3, or 2 categories, we actually got better scores. And so we have a land use model that is this 4-tier taxonomy. And then in addition to that, we trained a roads-only model. And this is how we did. So starting at the 2-category model, we were scoring 85% on down to the 6-category model, which was just under 70%. And the 6-category model itself, when we were looking at the scores, we felt like, well, maybe the 6th category isn't going to be so useful. And we still had the 4-category model, which does break up residential into informal and formal categories. But I'll show a use case later where it turns out there's a lot of useful information in the full 6 categories. Our roads model, we actually compared to 2 different data sets, one from Atlas of Urban Expansion and the other to OpenStreetMap. And in both cases, we separated the roads into kind of bigger, more important roads and then like smaller roads. And in both cases, we did pretty well on the big roads and pretty terribly on the small roads. Now, this isn't surprising because, most 2-lane roads, are barely 5 meters. So in fact, when you actually look at the results, it seems like we did quite good on the roads that you could see at 10-meter resolution. And this is what it looks like. Here's a built-up model, and this is Cairo. I picked it because I just think it's beautiful. And here's the same location as a 3-category model. And here's the same location at 4 categories. And then finally, here is the 6-category model. As mentioned at the beginning, we also use the outputs of our model to build an informal settlement classifier. And this was just taking out of the box Smile Random Forest from Google Earth Engine with 15 trees. And it did surprisingly well. Our final model, I'm using global here because, in quotes, because it was only 3 cities, scored 74% globally, which did pretty good in Mexico City and San Jose and not so great in Bangalore. But by training a Bangalore-only model, we got up to 64% and then 78% for Mexico City and San Jose. One of the things I wanted to point out here was we trained it using just the informal category and then on up to all 6 categories plus roads. And you can see each time we added more data and more detailed analysis of formality of these residential areas, we did a little bit better in our accuracy. So this is kind of an example of how, even though the accuracy itself for the 6-category model isn't great, it is useful for certain use cases. Okay, so that's it for my slides. I do have a short demo to show you. Here's a quick walkthrough of Earth Engine app we built. You can see we've broken the world up into a bunch of different regions. You can get data about that region by clicking on that. Here, we're going to look at Mexico City a little closer. Zoom in a little bit. You can also get reports like that on a city basis. And our results look similar to what you might expect. We have a lot of informal areas on the outskirts of the city with non-residential in the center. You can see we get a lot of fine detail on the roads here. Going off to this informal area, we've missed a lot of the roads. But we included the probability layer, and you can start seeing the structure of the roads underneath. And if you do a little thresholding, all of a sudden you can pick up all of those rows. And so, yeah, let's scroll around a little bit and zoom in and actually try to see what it looks like underneath. Are we actually doing something that makes sense? And you can see the larger, big industrial buildings are being picked up as residential, and the blue there is all, or non-residential, and the blue is all residential. And so it looks like it's doing a good job. You can also draw little polygons and get land use shares. And I've switched it over to the 6-category model here. So as I scroll out, you can start seeing more detail in the area you're looking at. So thanks, everyone. That's the end of my presentation.
Okay, thanks, Brookie. Our final presentation in this session welcomes 3 speakers. They are Albert Martinez Sequero is a climate security analyst at the United Nations Environment Program. Genevieve Patenaude is CEO and founder of Blox, and Iain Woodhouse is a professor at the University of Edinburgh. They will be presenting on how they've used Blox, powered by Earth Engine, for understanding climate stress.
Hi everyone, and welcome to our keynote on Strata, Earth Stress Monitor. My name is Albert Martinez. I'm a climate security specialist at the United Nations Environment Program, and together with me are my colleagues Genevieve and Iain to help me introduce Strata. Next slide, please. So around the world, we are seeing the impacts of climate change unfolding, threatening food, water, and energy supplies, damaging essential infrastructure, and even undermining livelihoods. In crisis-affected contexts, the impacts of climate change can intensify existing social and economic vulnerabilities, which in turn can lead into more competition over natural resources, displace people from their homes, and even exacerbate the root causes of conflict. So to be able to address climate security risk at a scale, there is an urgent need for improved and accessible insights into the links between climate change and peace and security. This will allow us to get better data-driven and science-informed policy and programmatic action. Next slide, please. So in this context, the United Nations Environment Program is developing Strata, a digital platform designed to provide climate and environmental security intelligence. Strata aims to allow practitioners and policymakers to streamline climate security insights into the daily work, enhancing monitoring, analysis, and even early warning of environmental and climate-related security risks. Next slide, please. The development for Strata is grounded in a strong partnership between UNEP, the University of Edinburgh, and Blox. And this is done in collaboration with the European Union, the Government of Norway, Google Earth Engine, and the Group of Earth Observations. Now I'm going to pass the floor to Genevieve.
Thank you, Albert. Hi, everyone. My name is Genevieve Patenaude, and I'm the CEO of Blox. I have 20 years experience in the use of Earth observation to monitor environmental degradation. I'm now focusing on driving the sustainability transition. At Blox, we believe that to achieve climate change and adaptation at scale, climate intelligence must be accessible at scale. And thanks to the incredible power of Earth Engine API hooks, data and processing capabilities are now available at scale. But intelligence is not. So getting insights from planetary scale data remains in the hands of a limited set of experts, those with coding skills, expertise, time, and resources. UNEP practitioners, those with boots on the ground, don't generally have those skill sets. So we need to give them access to climate security intelligence at the scale that they need. And this is why this partnership is working to build Strata. Blox brings into this partnership a powerful no-code and intuitive planetary data solutions builder, which empowers everyone create their own intelligence, code-free and with ease, giving everybody, the decision maker, analyst, field workers, the insight needed to drive positive change. And we're supporting Strata close the gap between the extensive intelligence that Google Earth Engine can offer and accessibility, so that those doing the work that really makes a difference in the various countries of the UN can rapidly and easily identify climate and environment environmental stress hotspots. That is, where environment and climate stressors converge over space and time, but also from local to regional scales. But also overlay those hotspots with structural socioeconomic risks, basically other potential drivers of displacement, social unrest, maladaptation, or even conflict. So those two combine, the stressors and the vulnerability exposure, can help really flag where communities are exposed to both those various forces that can exacerbate living conditions. Strata is ultimately designed to support practitioners accelerate the implementation of risk reduction, climate change adaptation, but also resilience building solutions. So here's a brief demonstration of strata in action.
In this example, we are looking at Somalia, and where meteorological and agricultural drought may be impacting large numbers of people, and where this coincides with security risks. By leveraging Google Earth Engine, we are able to utilize numerous sources of data on historical weather patterns to understand where drought is occurring. Then, by combining this with population data and accessing data on peace and security risks through an API connected to ACLED, we can understand the impact this is having on the people in these areas. The dashboard allows users to take a deeper dive into the data. Each indicator is scored based on a deviation from normal and weighted for the population exposure. Users can look at individual indicators and see how this manifests in different regions and districts.
Hi, so I'm Iain Woodhouse. I'm at the University of Edinburgh, and I'm just going to spend a minute or so telling you a little bit about the approach that we're using in Strata in terms of how we are combining these stressors that Genevieve mentioned. So here are our three baskets of indicators. So these are the factors that are the stressors on the environment. And these data layers have been chosen from a combination of literature reviews and feedback from the user workshops so that they match actual case studies and use cases. So there's climate and environmental hazards. These are the ones that are mostly from Earth observation data, and they're related mostly to the physical environment, flood, land change, weather. And then in addition to that, we have peace and security information that comes from the ACLED database. And then in addition, we have the socioeconomic exposure and vulnerability indicators. And what's really important about Strata is that we can access almost all of these data layers from Earth Engine so that we can draw that into the Strata platform. Next slide. And what we do with that then is we're using a convergence of evidence approach. And so this has got precedent and support in the literature in terms of this technique. And essentially what it means is that we are combining together these stressors, these indicator layers, by looking at whether or not they cross a threshold and then giving them a red flag. And then what we do is accumulate those red flags to look at our convergence map that produces the hotspot map. The vulnerability indicators, what we do is scale that between a minimum and a maximum across the country. And then that gets applied to our convergence map to produce the final output of the hotspot map. And then the dashboard that you saw in the video, that allows everybody to see the output data. And because it's an interactive dashboard, you can actually, the user can view different layers. They can see the combinations of the hotspots or the different factors involved. Next slide, Genevieve. Now, one of the key things in here is the choice of thresholding. So how do you actually choose the threshold on these indicator layers, the stressors? And that's one of the key challenges. And there's two main approaches that we use here. One is looking at trends in space. So is there a particular location that is statistically different from all the rest? And the other one is looking at trends in time. So one of the key things in how we extract data from the Earth observation information on Earth Engine is that we can look historically through any given minimum mapping unit. So the little pixel, we can actually look at the historical data to see if it crosses a trend, if something is is below the expectation for that time of year, and then that gets a red flag. Now, where we are now is that we've got a version 0.1 working. We've got a prototype. It's now being tested with users in Somalia and the UNEP team. And we're looking to advance that as we go forward. And I'll pass now to Albert to talk a little bit about that.
Yes, thank you. Finally, as a closure, we want to highlight and note, learn from our work all across the world. So we know that addressing the devastating impacts of climate change requires innovative approaches that are based on strong partnerships, creative thinking, technology, and science. Strata is harnessing all of this, putting data and insights into the hands of those who are working every day to build a more inclusive, resilient, and peaceful world. We're looking forward to launching Strata in January 2022. Thank you for your attention, and please do not hesitate in getting in touch with us, especially if you work in the nexus of climate security, whether that it's on data, research, or practicing. We would really like to hear from you. So thanks.
Thanks so much for joining us today, and let's kick off the Q&A. All right, those were some great talks. Thanks very much to the speakers. I'm here with nearly all the speakers, including Youchen, TC, Brian, Brookie, Genevieve, and Iain. Over the past hour or so, you've been asking some great questions, and now we want to give the speakers the opportunity to answer some of those. If you're in the audience, you can still submit your questions right below the video, and we'll answer as many as we can. So let's take the first question. The first question is for Youchen from Adam O. How did you migrate your models from R to Google Earth Engine?
Yeah, thank you, Adam, for your question. So as mentioned in the presentation, we use 3 model algorithms, which are supervised linear regression, geographically weighted regression, and random forest. So here I would not dive into details how the models work or how it were optimized, but in short, for migrating the first 2 methods, which are the linear regression models, we uploaded the coefficient values of the regression to the Earth Engine in a CSV file or a GeoTIFF format. And as for the random forest, we uploaded the optimized random forest hyperparameters to Earth Engine in a CSV format as well.
Okay, thank you, Youchen. The next question is for TC from Santiago. Hi, TC, thanks for your presentation. How did you select non-urban areas to calculate the urban heat island?
Thanks for that question, Santiago. In the current version of the algorithm, I'm using the 300-meter resolution European Space Agency Climate Change Initiative land cover data. The dataset is available yearly from 1992 to 2018, but in my case, I'm using it from 2003 to 2018. And for each urban cluster, I basically choose the pixels that are not built up and not a water body, and then use those to define the rural reference. Thank you.
All right, thank you, TC. Next question is for Brian from Richard. Does increasing albedo of roofs reduce warming more than using dark solar panels? And is the total roof area significant compared to, say, the natural variability of snow cover?
Yeah, thanks, Nick, and thanks for that question, Richard. I would say this is very much an open area of research. And I would really refer you to experts at Arizona State University or Lawrence Berkeley National Lab that are working on this question of increasing roof albedo versus solar panels. And there's a big question as to whether putting solar panels in cities may actually be warming cities at certain times of day. And depending on how those panels are mounted, there can be big differences in what the near surface temperatures are. At any rate, I would say that overall snow cover area is decreasing. We see that trend. And from TC and Brookie's work, I would expect that roof area is increasing. So definitely the opportunity for cool roofs are growing. Even if they're not a big lever for global climate, they can have a big role in mitigating urban heat islands like TC was talking about.
Okay, thank you. The next question is for Genevieve and/or Iain from Cesar. Is Strata open and free to use? And if so, is there a link to access it, and where can they get the link?
Right, I can take that question. So we're in the pilot phase of Strata at the moment, and the idea is that there is a component of Strata that, yes, is indeed free and open to use, but it's not yet at that stage because we're testing with different countries around the globe, and making sure that once we open it, it meets the job needing done of all the different UN teams and advisors that work in the UN countries.
All right, thank you. We'll go back to you, Youchen. Here's a question from Genevieve. What makes Google Earth Engine not fit to do algorithm optimization, hypertuning, etc.? And why did you have to do that in R instead?
Okay, yeah, thanks, Nick, and thanks, for your question. So for the two linear regression model, because we already have the R script and the packages are already available in R, so it doesn't make sense for us to spend time on writing code from scratch in Earth Engine. So that's why we did the model optimization in R. And for random forest, because we use the out-of-bag samples to optimize the hyperparameters, and it's also easier to do it in R than in Earth Engine. So that's why we use R for this task instead of Earth Engine.
Okay, thank you. Yeah. Next question for Brookie from Samira. Are the informal versus formal settlement data available in Earth Engine?
Oh, thank you, Samira, for the question. The informal data, I am 99% sure is. There's a chance we uploaded it, but they came from a number of different sources. And then for the formal areas, we didn't have a nice way to identify this as formal. So what we did is we took from all the open areas that is not formal, we generated little random regions. That is not informal. We generated random regions that were approximately close to the informal areas and approximately similar shape. So it kind of maximized the difficulty of distinguishing these two regions.
All right, thanks for that, Brookie. Going back to you, Brian, question from Christina. Which wavelength range are we talking about when we talk about albedo? Is it broadband shortwave or something else?
Yep, yeah, it's broadband shortwave, so about 0.2 to 4 microns. That's a short answer.
Yeah, and a follow-on here, also from Genevieve. How do you get albedo from Sentinel-2 surface reflectance? Yeah,
so another viewer made the important point that surface reflectance does not equal albedo. So there are narrow band to broadband albedo conversion algorithms or retrieval algorithms, and I think a Google Scholar search is a great place to start down that journey. There are a lot of papers published on using the Sentinel-2 data in that way. So I'd encourage you to start your search today.
All right, thanks. The next question is another one for Genevieve and Iain from Geody. Sorry for the pronunciation there. Thank you for the very informative presentation on Earth blocks. The Geody followed the link and found a page about nature-based solutions. And the question is, can you speak to whether you can verify carbon credits on your platform, or maybe just talk a little bit in general about how you could use the platform for establishing carbon credits?
Great, thank you. Thank you for your question, GOT. So the main, not obviously every carbon credit can be verified using our platform. There's all sorts of different ways to get carbon credits, and we're speaking specifically about nature-based solutions, and in particular about forest-related projects, so land use change, and forestry. So it's mainly to monitor the progress of project, to select project, but also to assess the risk and whether you've complied with your prediction on your emission reduction. So it's continuous monitoring.
All right, thanks. Another question for TC from Emil. Great work, TC. Can you share any documentation about the simplified urban extent algorithm that you developed?
Thanks for the question, Emil. So there was a paper that we published which documents the algorithm. I think Karen is gonna paste that on the chat, like after your question. I'm also writing like an update to that algorithm, which is going to be published through the Columbia CDAC archive. So I want to let you know, I guess, when it's done. Thank you for the question.
All right, thanks. Another question for Brookie from Adam. Adam is interested in the tool that you used to reduce scripting required to call VMs. Is that tool available? And if so, where can they find it?
So it is in my GitHub account. I think Karen is going to post that as well. But it's Brooke is me. And then it's called AI Plat Go. But just to clarify, it's for launching jobs and AI platform jobs. All right, thanks.
Another question for Genevieve and Iain. Thank you very much for the Earth blocks presentation. As I understood it, pixel-based time series are used as flags. How do you ensure that the flags are not caused by outliers in the data?
Okay, I can take that one. It's usually collections of pixels, so it's rarely an individual pixel over time. So we're looking at the area averages. So if we're looking at deforestation, it's not an alert to say we think some deforestation has happened. There will be a time period over which you're looking and an area average to say in this region there is more deforestation than normal. So it's typically not done at an individual pixel, so that we avoid exactly that challenge that you picked up, is that you might just get the occasional stray pixel.
Great, thanks. Another question for Brian. Have cities or municipalities started using the tool that you developed to do things like prioritizing buildings for increasing rooftop albedo?
Yeah, they certainly have. And Reflective Earth has started to do some pilot work with cities around the US and indeed around the world to not only pick out buildings where there's a large opportunity, maybe it's a large roof, but also to really zero in on areas from a justice perspective that are experiencing extreme heat. Think of the work that TC is doing, combining some of these data sets really offers a unique opportunity to really intervene in the right place at the right time and to create these outcomes that we all want.
All right, thanks. Another question for TC from Giodi. Fascinating presentation. Wondering if you'd looked at the impact of individual trees lining streets or the impact of trees in general.
Thanks for that question, Jyoti. I have not, and that's actually a very important question when we want to use these data for actual on-the-ground policies. But our results are pretty broad scale. I think a bigger issue might be how the temperature change due to tree cover in land surface temperature translates to temperature change in air temperature and heat stress. And there's a lot more work to be done at the local scale to get that answer.
All right, thank you. Well, it looks like we got to most of the audience questions here, so I'm just going to throw one more softball question to everyone. The common theme here was, of course, Earth Engine. And so the question to the speakers is, what's the one feature that you would really, really like to see in Earth Engine, and why would that help? Brookie.
I was hoping to not go first, but there was lots of questions for Youchen about getting algorithms back into getting things from R into Google Earth Engine. And, you know, when we were doing our informal settlement classifier, we were just using the kind of, you know, the off-the-shelf random forest, and it worked great, but just saving it and getting it back in is still kind of this, you export the R text file and then you're bringing it back in. It would just be great to be able to save your models there and run them there. I actually find it trains extremely fast and you can't get all those out of bag estimates, but just having a smooth pipeline for keeping those model classifiers saved in Google Earth Engine.
Yes. Thank you for that. We are working on it. Youchen, anything to add there?
Actually, yeah, like as mentioned earlier, I think algorithms being safe is really a great step forward for our work. And also, I would like to see like OpenStreetMap data available in Earth Engine, because we kind of use a lot OpenStreetMap data for representing the point emission sources as a proxy for air pollution modeling. So that would also be great if in Earth Engine data catalog we can access OpenStreet data.
Yeah, that would be great.
Yeah.
TC.
So I had both one point about the feature and the data sets. So for feature, I think one would be being able to upload image collections at once. And right now, the way to do it is through, you know, third-party modules. And the other is for, I don't know currently, at least for the JavaScript API, I keep having to convert my GeoJSONs to shape files and then uploading them. So there was a way to directly upload the GeoJSONs. And for data sets, there has been a lot of work there. So the ERA 5 land, NCEP Incar, all of that has now been archived on the data catalog.
Yeah.
But there are quite a few other both reanalysis data products as well as climate data products, like from the CIMIP 5 and CIMIP 6 model runs. Having those data, including like future scenarios, would be useful.
Okay, good. Well, we'll work on that stuff. Unfortunately, we're running short of time, and so I'd like to thank all our speakers and thank the audience members for your great questions, and thanks to everyone out there who's watching. Please join us for the next session, and I hope you have a great summit. Thanks again.